When we look at the night sky and ponder the scale of our galaxy, the universe, or even the multiverse, are we closest to sentient monkeys gazing up in wonder on the savannah? Or are we more like gods contemplating the cosmic machinery that we've built? Or are we most like bacteria, multiplying across an infinite series of petri dishes? Recent discoveries about the nature of the universe suggest we may have more in common with these humble bacteria than we once suspected. But to understand why, we have to explore our relationship with the cosmic distance scale and how it's evolved through the ages. To 1920, when two scientists were pitted in a cosmic battle, what is the true size of our universe? Ancient astronomers had long observed strange shapes in the night sky, bright luminescent arms and arcs glowing in the darkness. The most famous one of these, the Great Spiral Nebula in Andromeda, fascinated astronomers for generations. Harlow Shapley of Mount Wilson Observatory argued for what at the time was the mainstream hypothesis. These spiral nebulae, like Andromeda, were simply dust clouds at the edges of our Milky Way galaxy, which back then was believed to contain the entire universe. His opponent in this great debate was Heber Curtis of Lick Observatory in Northern California, who proposed something radically different. These weren't dust clouds in the Milky Way at all, but each one was an entire island universe. Each cloud a separate galaxy, just like our Milky Way. But for this to be true, the scale of the galaxy implied that they must be impossibly farther away than ever considered before. The debate was inconclusive for another 3 years, when Edwin Hubble, using the powerful new 100-inch telescope at Mount Wilson, made a discovery that changed everything. His observation of special type of pulsating star called Cepheid variables within the Andromeda Nebula proved that it wasn't a nebula in our galaxy at all. It was far beyond our own galaxy, millions of light years away, an enormous city of billions and billions of stars, and it was located 2.5 million light years away. Think about that. Overnight, on a cosmic blink of an eye, our galaxy grew from one galaxy to literally billions of them, each containing hundreds of billions of stars themselves. But this raised a new question. If we were surrounded by these cosmic lighthouses, what was the energy source that powered them all? Physicist Hans Bethe was faced with a puzzle that had stumped scientists for generations. How could stars possibly generate enough immense energy to last for billions of years without burning out? The prevailing theory of the time suggested that stars were powered purely by gravitational collapse, the pressure of gravity, like an invisible hand, compressing the star to collapse on itself. While this is a true phenomenon and it's important to star formation, Bethe and his peers knew that this process was inadequate to the task. It could only power a star like our sun for about 20 million years, and we already knew the Earth was much, much older than that. Instead, Bethe proved that stars are actually cosmic nuclear reactors, fusing hydrogen into helium and converting mass into pure energy. Einstein's famous E=mc² equation in action, a mechanism that could explain not only the star's incredible luminosity, but also their longevity that would make Peter Attia jealous. This leads us into the third great debate. New techniques called radiometric dating could now precisely measure the decay of radioactive elements. This turned ancient rocks into cosmic clocks and revealed that the Earth was 4.5 billion years old. There was just one problem. Edwin Hubble had also discovered that the universe was expanding, with galaxies moving away from us at enormous speeds proportional to their distance. This is what we now call the Hubble relationship. The velocity is proportional to the Hubble constant times the distance. Based on the expansion rate that he observed, the universe would be younger than some of the objects within it, including the Earth. This would be like you finding out that your mother is younger than you. Now, Walter Baade came to the rescue. He showed that Hubble had measured the cosmic distances wrong. That updated the Hubble constant and proved that the universe had been expanding for much, much longer than Hubble originally calculated. Now we know the universe is some 14 billion years old. Plenty of time to create objects like the Milky Way and Earth itself. But this didn't settle everything. In fact, it launched the fourth great debate. In the 1960s, most scientists believed that the universe had existed forever. Unchanging is called a steady state model, where matter was continuously generated to fill in the gaps as galaxies moved apart from each other, and that kept the average density of the universe constant. But it had always been there. That is until 1965, when Arnold Penzias and Robert Wilson, two physicists working at Bell Labs in New Jersey, made a startling breakthrough, discovering something serendipitously. And that was a background noise that appeared to be in the microwave radio antennas that they had built to measure the first communication between early satellites in the early 1960s. This persistent, unexplained radio noise seemed to come in all directions, day and night, and it couldn't be removed. After consulting with Robert Dickey and his team, including my PhD advisor's PhD advisor, David Wilkinson, they realized that the static was actually the cosmic background radiation, the cooling remnants of the previously hot dense universe, which had expanded over billions of years, cooling off from tens of millions of degrees to a mere 3 degrees above absolute zero. But what caused the universe to come into existence from the beginning? Which brings us to the fifth great debate, still raging today in 2025. When three physicists, Paul Steinhardt, Andrei Linde, and Alexander Vilenkin, realized something extraordinary about the first moments of cosmic inflation. Cosmic inflation describes the period of incredible expansion in the universe's first trillionth of a trillionth of a trillionth of a second. Vilenkin and Steinhardt and Linde suggested that inflation wouldn't just create one universe, it would have to generate an infinite number of universes. Physicist Alan Guth, the father of inflation, called it the ultimate free lunch, an infinite number of universes emerging from practically nothing. In the inflationary scenario, each universe is like a bacterial colony in its own petri dish, growing and evolving in isolation, separated by vast expanses of space-time. Each dish could have its own completely different laws of physics and completely different constants of nature, resulting in unimaginable possibilities of what can possibly exist. But this creates a profound problem. If anything is possible in this infinite ensemble of universes, any theories about the nature of creation itself? Have we reached the limits of what science can tell us about our cosmic origins? Some say this theory is dangerous, not only for science, also for society, which depends on the scientific method. This fifth great debate is still in progress, and one answer to it may lie here, in Chile's Atacama Desert, at 17,000 feet, one of Earth's highest and driest places. This is the Simons Observatory, and with it, we're looking for something called B-mode polarization, a subtle twisting pattern, a curling pattern of light's polarization, of the CMB radiation left over from the Big Bang. This polarization pattern, B-mode signal, would provide the strongest possible evidence for cosmic inflation, and also the first direct evidence of primordial gravitational waves from the universe's first instance of existence. If we can observe these patterns, it would be the strongest evidence yet that the multiverse is what its proponents claim it to be. But until the dust settles on our final cosmic debate, we must return to our initial question. What is our place in the universe? Is it designed uniquely for our existence? The constants of nature, like the strength of gravity or the mass of the electron or the speed of light, are they as precisely calibrated and tuned for our existence as they seem to be? In the world of the multiverse, are they simply the result of a cosmic coin flip? One day, hard data may solve and settle the fifth great debate. But in the meantime, one thing is for certain. As humans, we'll keep asking questions. We will keep pushing, aware of our own limitations, but never ceasing to seek, but seeking to perpetually expand our understanding. Beyond each cosmic horizon, one debate at a time, until we arrive into the impossible. I'm Brian Keating, and if you'd like to dive deeper into the cosmic controversies of the multiverse, check out my conversation with one of the godfathers of the multiverse, Andrei Linde, where we explore first seconds of the universe's existence. Thanks for watching, and remember, the greatest debates in science aren't always about finding the right answers. They're about asking the right questions.